Hey, hello class. I'll try another video solution here. It's chapter 21, number 22. And in fact, let me encourage you, not that it's needed, but the description of a four-stroke engine is given in much greater detail in chapter 22. But they give you enough information here to go ahead and solve this problem. But I think to kind of deepen your understanding, you might want to look at chapter 22 first and the four-stroke engine. But in either case, let me read this. It says, during the power stroke of a four-stroke automobile engine, the piston is forced down as a mixture of combustion products of air undergoes an adiabatic expansion. Assuming 1, the engine is running at 2,500 RPMs, or cycles per minute. Number 2, the gauge pressure right before the expansion is 20 atmospheres. Okay, number 3, the volume of the mixtures right before and after is 50 and then 400 cubic centimeters respectively, and then they have a little picture there. And then number 4, the time interval for the expansion is 1/4 of the total cycle. And that's the part that would make more sense to you if you read about the four-stroke engine, that 1/4 of the cycle, one of the 4 strokes, is the power stroke. And so that's how we know the timing, or how long it takes, because we've got the number of cycles and then the timing here. Okay. And I should be careful. Notice they say cycles and not revolutions. But 5, the mixture behaves like an ideal gas with a specific heat ratio of about 1.4. Now, 1.4 is the molar specific heat ratio for a diatomic gas. And that makes sense because probably most of the stuff in that engine is nitrogen, and then the small amount of oxygen and fuel that burn heat, and the expansion is then being really driven by the expansion of nitrogen. Find the average power generated during this stroke. Okay, well, the first thing that pops into my head is PV to a gamma equals a constant. That is the adiabatic process. And if I look closely, they've given me initial values, or at least, initial values, at least a volume. I don't think they gave me initial pressure. But keep in mind, that would also mean that final pressure times final volume raised to a gamma would be that same constant. So if we set the two equal together, we get initial pressure times initial volume to a power of gamma is then equal to final pressure times final volume to a power of gamma. And as I go back and read this, especially number 2 here, it says the gauge pressure right before the expansion is 20. So the initial pressure is 21 atmospheres. Now notice I added 1 here because I want the absolute pressure, and they gave me the gauge pressure. And the gauge pressure is the pressure above atmosphere. So I'm going to put 1 atmosphere here for my initial pressure. Then the initial volume, they said, was 50 cubic centimeters. And I'm going to go with the non-conventional units. We're not talking about energy here, at least not yet. That's coming. So I'm just going to go ahead and use the units of atmospheres and cubic centimeters. That way the other side would be in atmospheres for the final pressure, which I don't know, but I do have a final volume. Oh, and raised to a power of gamma, 1.4. So if I grab my calculator, I can figure out then what the final pressure is. Why don't I... Actually, I'll move that over to there, because that then really is 50 divided by 400, and that ratio is then raised to 1.4. Then I can multiply that by 21 and get a final pressure of 1.14 atmospheres, which might be better written as pascals, 101,300, given that they are asking for power. Okay, so final pressure is 115,745 pascals. All right, I'll keep that in mind because they're asking for the power, and of course, power is defined as the rate at which work is being done. So work divided by time. I'll just write it as W over T. Now, the reason that's important is the first law of thermodynamics says that the energy you add to your system, when you add it together, that's the equivalent to the total internal change. And you could add energy by either heat or with work. But for the adiabatic process, there is no heat being added. So this would say that the change in internal energy is the work. And the work is what I'm looking for. And the change in internal energy is a state function. And so even though I do not have a constant volume problem in this, not even close. It's obviously expanding to push the cylinder down. I can still use this very famous equation, and so keep that in mind that anytime we're trying to find delta E, we can use the one that we derived for constant volume. In fact, maybe just to repeat, if you look at the first law of thermodynamics, and let's say you did have, I'm not saying we do have in this problem, because we definitely do not have, but if we did have a constant volume one, we would say no work is being done. And we know how to calculate the heat during constant volume. It's NCV delta T. So that tells us the equation for delta E is NCV delta T. And since this is a state function, we can use it for any of the other processes. And that's what I'm really doing. And so to me, it always looks funny, and I always like to give students a little warning here, that even though we don't have a constant volume problem here, I'm using the symbol constant volume in order to calculate the work. Not because it is a constant volume problem, but because work then is equal to delta E, and then delta E is equal to this, which is proven during the constant volume process. So that's how this CV comes into play. And like I said, we're not even doing a problem with constant volume, and yet it has it in there, and that always just seems a little weird. Well, I'll keep going, because if you then remember that PV equals to nRT, you could rearrange this or rewrite this, if you will. In fact, you did a problem, or it's coming up a little bit later. Yeah, it's number 43, where you're asked to show that this is equivalent to something else. You're asked to show that this is equivalent to 1 over gamma minus 1, final pressure times final volume, minus initial pressure times initial volume. And of course, that's what we have here. And so let me make that same kind of step that what you're going to do in 43, or maybe you already did do in 43. And let me just jump over here and then to a page 2. But if I put page 1 right above here so I can see this, I could write something like this. Using the N and the T, put there, and I'll just leave the CV alone for a moment. But this would be N times the temperature. And the number of moles times the temperature would be PV over R. PV over R. And this would be final and final, and then this would be minus, again, PV over R, but this would be initial and initial. And so this right here becomes CV over R. And then this would be final pressure times final volume minus initial pressure times initial the volume. And we could probably just continue with this problem by plugging those in because we know what those are, but I'll go ahead and then write it, what it's, I guess I'll say designed for. We could then write R as CP over CV. And then if we bring this CV under each, we're left with a 1 on the top, and that would be gamma, because that's CP over V, minus 1. And then we get final pressure times final volume minus initial pressure, initial volume. So we don't really know, at least going in this direction, what the final temperature is, or initial temperature, because we don't really know how many moles we have. So I'm not going to solve individually for the number of moles or the temperature change, but I am trying to point out the N and the T together are represented with the P and the V, and so we do know that, and that's what shows up here. So if I do that, then the gamma they said was the 1.4, and the final pressure, as we just worked out, was the 115,745 pascals. That's what we did using the adiabatic process. And the final volume, and let me be a little careful here. Maybe I'll come over here to the side. It was 400 cubic centimeters, which that means 400 centimeters cubed and meters cubed. You see in the centa is 10 to the minus 2, so you cube it, you get 10 to the minus 6. So if I'm going to put in my pressure in pascals, then I want to put my volume here in cubic meters, because pressure in pascals times volume in cubic meters comes out in units of joules. Okay, now the other pressure, which is the initial pressure, which we wrote as 21 atmospheres, we never worked it out in pascals. So let me take the 21 and multiply by 101,300 and come up with the pressure in pascals, 2,127,300 pascals. And then times a volume of 50 times 10 to the minus 6 cubic meters. Doing the same logic, a cubic centimeter is a centa cube, that's 10 to the minus 6, and then a cubic meter. Okay, so if I now grab my calculator here, let me take the 115,745 and multiply that by the 400 times 10 to the negative 6. So that's like about 46 and change joules. And then minus the 2,127,300 times the 50 times 10 to the negative 6. So these two together looks like is a negative 60 joules. I guess times 1 and then divided by, and it looks like 1.4 minus 1 is a 0.4. And so we're looking at a negative 150.2 joules. So notice the negative sign. That's good in terms of an engine, because that means energy is coming out of the gas, and in this case going to the engine, which of course then is what makes the car go. So the negative sign is energy coming out of the gas. Now to get power then, the last thing we need to do, since power is work divided by time, is to say, all right, and maybe I'll just do absolute value. So this is 150.2 joules of work during that 1/4 of a cycle. Now, maybe I should write it here, but the problem makes it very clear that this engine is doing 2,500 cycles per minute. Or maybe put another way, this is 2,500 cycles in 60 seconds. So if I go 25 and divide by 60, we're looking at about 41 2/3 cycles per second. And of course, then the reciprocal of that, right, would be the amount of time per cycle. Okay, so 1 divided by that last answer means that we're looking at 0.024 seconds for 1 cycle. Now, they also make it very clear that in a 4-stroke engine, there's 4 things going on. And so if this is the whole cycle, then we want a quarter of that. And let me say it again for those of you who know a little bit more about engines. This does not say RPMs because there would be 2 revolutions for each cycle. So if we're doing 2,500 cycles in a minute, I guess that it would be 5,000 revolutions per minute. So that's a little side note there. Okay, so anyways, this is the amount of time per cycle. So let me take 1/4 of this. So if I divide that by 4, we're looking at 0.006 seconds for the power stroke. Okay? And that then is the time. So I can bring that back up to here and go 0.006 seconds. So now I can see the power during the power stroke. And so this is 150.2 joules in a 0.006 seconds, making it looks like 25,000, and maybe I'll just do those 2 or even call it 3 significant figures, joules per second. I suppose I could even call that a watt. And so that's the power being released during that power stroke. Now, that's not the average because there's another 3 strokes where either no work is being done or actually negative work is being done. You're taking energy from the car, the rotation of the engine, and giving it to the compression. That happens during the compression stroke. So the average for my engine is going to be much, much lower than this, but this is the average power during the power stroke. And sadly, the other 3/4 of the time, got to average that down and even take some energy away. All right, hope that helps.